All right, everyone. Welcome to our final and third talk of the morning. It's my great pleasure to introduce Elena Giorgi from Columbia University. We're very happy to have her in person today, and she'll be talking about the amazing work that she's been doing on the stability of charged black holes. Elena, please.
Thank you, Martin. So okay, you can see me. Okay, so I'll just see. Thank you so much I want to start by thanking the organizers and Martin in particular for organizing this such an interesting and really wonderful conference. And it is really my first talk in person since for the last 2 years. So I'm very excited. And okay, so in this past few days we heard a lot about stability already. So I'll jump in immediately on the charge part. So why? Let's see. Yes. Okay. So let's see. I'm gonna try to motivate why we should look at also the charge case as an interesting aspect of the problem of stability. But okay, just to start slowly. Of course, I'm gonna write down the Einstein equation to start with. I'm only gonna consider zero cosmological constant case, so that there's already some. Oh, please stay close to the laptop. Okay. Yes. I'll be here. Okay, thank you. Okay, so I'm gonna write, this is the Einstein equation for a zero cosmological constant. We all know many properties about this equation, and also we also know that the simplest possible case is when there are no vector fields, the identically zero. This reduces to the Einstein vacuum equation. And you may have heard the sentence that says something like the vacuum case already contains all the difficulties. Like if we study the vacuum case, then we're good to go for all the other many other cases. And this is partially true, in fact. I mean, especially if you think about the geometry of the space-time. So the geometry of solutions to the Einstein vacuum equation, those are solutions to other kind of matter, have like very similar properties. But what I want to argue here is that the analysis of the equations that are resulting from the stability of these black holes and instead are different in the case of the presence of matter. And so what is the first kind of matter I'm going to consider is really the case of the Einstein-Maxwell equation. So when the gravitational field is interacting with electromagnetic radiation. Okay, so if I want to add colors to the equations, like quite literally, the first thing I would do would really consider this first complication that transfers from the Einstein vacuum equation to the Einstein-Maxwell equation, where of course the right-hand side of the Einstein equation is not zero, is given by quadratic expression in terms of the electromagnetic tensor that satisfies the Maxwell equations. And of course here you can see I added some color. I added color to the equation, so I also added difficulties. So now I want to really motivate why we should consider this more difficult case, not just for the sake of doing something more difficult. And so why study non-vacuum? Well, if you want, of course, a simple motivation may be that the universe is non-vacuum. It's clearly non-vacuum, but to be more, specific and trying to also to attain something that is, look at something that is attainable from even mathematical, physical, even understanding point of view. We can, as a motivation, we can start with the observation of LIGO in August 2017. Of course, we probably all know about the detection of gravitational waves, but in 2017, LIGO observed gravitational had some detection of gravitational waves that were a bit more special because they came from the merger of two neutron stars. And what happened is, what was really interesting, and from what I understand, it is still the only such observation, or maybe just in the last run, I'm not sure, but from what I understand, it was very special. Just 2 seconds after the gravitational wave signal was detected on Earth, a flash of gamma rays was detected in space by the Fermi satellite. And what they realized is that these two signals were coming from the same really tiny corner of cosmos. And so these were two different signals from the same cosmic event, one gravitational wave, one electromagnetic rays, and it's sort of that's what now people call it a multi-messenger astronomy. So they hope to build a sort of large template of this kind of observations that would be very rich, because we had the same event is giving two different signals. And so here you see in this signal there was an interaction between gravitational waves detected by LIGO, electromagnetic rays detected by the Fermi satellite. And why is this any relevant? Well, because the merger of two neutron stars is expected, from a theoretical point of view, to collapse into a rotating and charged black hole. So here, this is some simulation from this paper by one of the authors is Elias Moss from the Princeton Gravity Initiative, and you see here. If you what they're considering is a collapse of neutron stars. If you're in the spherical symmetric case, then you have magnetic field that is expected to disperse very quickly, and that's why people don't really consider charged black holes in the picture of LIGO, for example, in detection of LIGO, because the magnetic field is expected to disperse very quickly, and you can see in the spherical symmetric case, indeed, it does disperse very quickly. There is nothing left at the end. But if you're in the rotating case, if you remember from physics class, if you have some magnetic field that rotates, it creates electrical charge, and then the magnetic field does still disperse very quickly, but the electric charge remains at the end of the collapse. So you do expect to have some charged black hole at the end, some collapse to Kerr-Newman. And even without going to neutron stars, so that you could say those are strange, very complicated objects. We don't really know much about them. Even the merger of two black holes could be charged. So there have been works. So this one here, last year, and this more recent here, where they compare even like the first observation, so the one in 2015, that's still the loudest observation that LIGO did. And they compared the waveforms computed with a black hole that is charged, and they can see that the signal that was detected in 2015 is actually compatible with having charge to mass ratio as high as 0.3. So even the merger of two black holes could be charged. I mean, it is still compatible with the observation. Okay, so hopefully I motivated you. I gave you some interest now in going and see what happens when you add charge to the picture. Luckily, there were so many talks before me that already introduced lots of objects and the concept of stability. So I'm going to be very fast here by reminding you what is the family of black hole solutions. Okay, the first one is not a black hole, of course, Minkowski spacetime, and then in the vacuum case we have the Schwarzschild spacetime. We heard a lot about it. The Kerr spacetime, we heard a lot about it too. So we have the spherical symmetric and the rotating case, and now the Maxwell version, so the Einstein, the electrovacuum cousins of Schwarzschild and Kerr are Nordstrom and Kerr-Newman. We've heard about them too, because we've heard about extremal black holes and this conference. So I'm not really gonna say much more than Nordstrom is a spherical symmetric case. Kerr-Newman is the full general rotating and charged black hole. Okay, so we also heard a lot already about the stability problem, so I'm not going to again. I'm not going to repeat what is the stability problem per se. Of course, I'm just going to say that concerns a long-time behavior of solutions to the Einstein equation, which are perturbations of non-solutions. In particular, there is the stability of Kerr-Newman family conjecture. Again, we've heard about it already. That says that if you perturb the initial data of a Kerr-Newman black hole, this perturbation will evolve to something that in time is going to converge to another member of the Kerr-Newman family. And so, of course, since you've heard already many talks about this, you're kind of convinced that this stability conjecture is true. But if you didn't hear about this talk, well, you could ask, well, why should we believe it's true? Well, there are some clues to stability that have been accumulating in over the past decades. If we go back to the 80s, the work of Whiting, we have the mode stability. It's the first clue to stability that says that what could be terribly wrong, which mean exponentially growing modes, are not present in the Einstein equation in Schwarzschild, Nordstrom, and Kerr. So there is no such work coming from back then for Kerr-Newman, and we're going to come back to this at the end of the talk. So this is for the mode stability case. So the first step. Then about the linear part of the equation, in the last 10-15 years already, also lots of works have been done about the scalar wave equation on black hole backgrounds by many people, starting with K. Wald, Blues-Hoffer, Dafermo, Słoniawski, Tataru, Donano, Anderson, Blue. There's so many that I can't possibly not really nominate, like mention everybody. So lots of people worked on the scalar wave equation. What it really tells us is that the linear part of the Einstein equation could possibly be well behaved. And what about the nonlinear part? Well, the clue to stability, the reason why this was believed, let's say a few years ago, before many other works have been done, that this conjecture was true, is also that the nonlinear part is expected to behave in a good way, which was done in the proof in the 90s, and the nonlinear stability of Minkowski space, Aristotle Kleinerman. So these were the clues to stability, let's say something like 10 years ago, but now there are lots of results, actual results in the stability of Einstein equation in black hole background. So Schwarzschild space-time has been the first to be looked at, and has been proved to be linearly stable to gravitational perturbation, but first by the Fermo-Solz-Zeroniaski, then other proofs that followed. And for the nonlinear stability, there was the work of Kleinerman-Sheftel under a class of symmetry, axially symmetric polarized perturbations, and the Fermo-Solz-Zeroniaski-Taylor that we heard about for the full picture with the dimension 3 submanifold. Then for the Kerr case, there have also been lots of works in the past few years, and the Fermo-Solz-Zeroniaski and Ma were the first to look at the Tokowski equation for small angular momentum, which is the first step in a certain sense of the linear stability. And then there have been other approaches by Anderson, Bartal, Bluma, Hafner, Inservasi to control the full linearized gravity using Newman-Peano's formalism, using harmonic gauge. So we heard about some of these works in this conference. And of course, then there's work of Schwab-Vento, Frotman, Teixeira da Costa for the full subextremal case. And for the nonlinear stability, we've heard about Serge's talk. So I'm not going to, again, mention more about that. What I want to talk about is actually the electrovacuum case, which is the Rice-Nordstrom and the Kerr-Newman metric. And so that's what I've been doing in the past few years since my PhD. And that's what I want to state, the theorem for the linear stability of Rice-Nordstrom, just to give you an idea. So this theorem, it's really, you can say it's a copy paste of the theorem of, if you want, I mean, the statement, it's a copy paste of the theorem of the Fermat-Zeroniaski in the case of Schwarzschild, and this is in the case of Rice-Nordstrom. So it says all solutions to the linearized Einstein-Maxwell equations around Rice-Nordstrom. So here I didn't say, but this is proving the full subextremal range, remain uniformly bounded on the exterior and decay to a linearized Kerr-Newman solution after adding a pure gauge solution, which can itself be estimated by initial data. So you may recognize some of the words here, in particular, especially from Martin's talk, where you see that the decay is conditional up to this Kerr-Newman solution, this pure gauge, and this is something that was already mentioned before. And again, as an aside, I'm going to remind you that when you linearize the Einstein vacuum equation, but if you linearize the Einstein-Maxwell equation, it's the same thing around a solution. Well, you will always have two sources of instability for this equation. One is given by the fact that the Kerr metric is also a solution of your Einstein vacuum equation, and so if you change the metric by mass or an angular momentum, this will still be a solution. And the other source of instability, even more problematic in general, is that this is a tensorial equation. So an equation that is true for a tensor is true. So if it's true for a metric G, then it's true also for every pullback of the metric to any diffeomorphism. So there is a huge gauge freedom that is going to be a source of instability. So again, we've heard about these problems, and so just what I want to say is that you should expect to have decay up to a change of parameters and a choice of gauge. Okay, so the steps of the proof, again, in a certain sense, it also follows. It follows like the proof of the Fermat-Zeroniaski. I mean, it has a similar flavor. In particular, it is very, very roughly speaking, divided in two parts. First, you want to control the gauge invariant quantities, so quantities that are not so much dependent on the choice of gauge. In particular, in the linear theory, they are independent of the choice of gauge. And these quantities will satisfy some Tokowski type equations that you hope to control and and really obtain boundedness and decay for such quantities. And this is something that is sort of separated from the second part, but the second part is still, what is left to do is that after you control the gauge invariant quantities, well, you still have to control all the other quantities, which are gauge dependent. So that's where the gauge is really, crucial. I mean, it changes depending on the gauge. It changes completely, the structure and the hierarchy of your equations and so on. And that's where you want to identify the residual gauge freedom, the Kerr-Newman parameters, and so on. So these are very roughly the two aspects of the proof, and try to say a little bit about both. So let's start with the first part, of really the setup. And I'm not going to spend much about it because we've heard already what is the setup of this kind of problems. This setup, this formula really goes back to the stability of Minkowski space, Resolutive-Kleinerman. What you have, you start with foliating your space-time with two surfaces, and you have a null frame associated to each point. So your null frames are E3 and E4, which are normalized to their dot product is -2, and you have this kind of picture, these two cones that intersect on the surfaces. And what you want to do, why do you separate why do you have these frames where what you want to use these null frames to decompose all your quantities with respect to the null frames. So you start with your Ricci coefficient. So let's say your chi, which is the second fundamental form. You have your Weyl curvature, and in the case of the Einstein-Maxwell, you also have the electromagnetic tensor. So you also decompose the electromagnetic tensor. And here I wrote in red, this alpha and alpha bar, because we have again we've already seen in C1 Stock, in Serge Stock, Martin Stock, we'll see that these are the quantities that satisfies the Tukowski equation, that are gauge invariant. And here, the beta f then is the equivalent of the alpha for the electromagnetic tensor, and these are also the quantities satisfy the Tukowski equation if you look at a Maxwell theory only. Okay, so if you look at the Maxwell equations on let's say on fixed Kerr background, they satisfy the Tukowski equation. But now here we're actually looking at the coupled electromagnetic gravitational perturbation, so it's not going to be that simple anymore. Just as a reminder, why maybe really in the first place why we use such a long formalism and so many Greek letters and so many equations to do all this. Well, the reason, and why don't we use coordinates, for example? Well, the reason is really, I mean, at least the way I really motivate myself to do all these computations, really that there is one very good reason, that is that the Kerr-Newman family admits a special null frame, the principal null frame, which is given explicitly by this E3 and E4, that diagonalizes the curvature, the electromagnetic tensor, diagonalizes most things. So you have all the alphas and the beta f are all 0. The only quantities are non-zero are the mid quantities of the curvature and electromagnetic tensor, so rho, sigma, rho f, sigma f. And since it's easier to linearize around 0, that's it is a good starting point to start with this null frame as opposed to a set of coordinates. In general, it is easier. And in fact, it is it is well known since the 70s, as shown by Tukowski, that the symmetric to tensor alpha and alpha bar satisfy what is called the Tukowski equation, which is decoupled by everything else. And it's the structure of this equation is the D'Alembert, and then it has some first order terms of the form nabla dr, nabla dt, nabla d phi, and a potential. And this is what physicists back then were studying to prove most stability and so on. But if you want to study that general solutions to the equation, well, you have a problem even in Schwarzschild. It's not clear how you would study directly solutions to the Tukowski equation, and that's something that we heard from Martin Stock, Serge Stock, that there is a way even in Schwarzschild. So there is this issue, and what was found by Dafermo-Solzhenitsyn is a physical space version of the Chandrasekhar transformation, which is this transformation that takes the Tukowski equation and gives you a Reggie-Wheeler equation, which I would call a Reggie-Wheeler equation that is only given by the inversion and a potential. And so this is called Reggie-Wheeler because this is in fact the equation that in Peter's talk was mentioned. It's this equation it's a similar equation that's satisfied by the metric component of components or in the perturbations of Schwarzschild. And in fact, there is a relation here. It's sort of hidden, But what is this transformation? What is this magical transformation that brings, a bad equation, let's say relatively bad equation, into a good equation, when it's a transformation that consists in taking two null derivatives. And here I'm going to write very schematically how it is obtained, with some rescaling in R, but I'm not going to say any details about that. But what what you should just have in mind is that to cure a bad equation, to make a bad equation become a good equation, you need to take two derivatives, which seems a terrible idea, right? If you start with a bad equation and take two derivatives, it sounds like a terrible idea. But in this case, there's so many hidden. There's some hidden structure, and in fact, if you do this computation, which I don't necessarily recommend, but if you do it, you see there are lots of cancellations happening, and you sort of recover the metric equation, the equation that was obtained from metric perturbation, from the one obtained from curvature. So there is some hidden structure there. But once you so this was found by Chandrasekhar in the mode decomposed picture, and by also Roniaski in the physical space picture. And in the once you have an equation with just a D'Alembert potential and a good positive potential, I should say, then this can be studied pretty much like a scalar wave equation. So, and you can apply the vector field method and obtain lots of many things, also the decay and properties about this red Q, and then you can deduce from alpha. You can deduce from Q informations about alpha from the differential, the way Q is defined as a differential, so as two derivatives of alpha. Very roughly, that's how it goes. Now, what about Kerr or Kerr-Newman? Well, the crucial difference here is that the principal null frame now in Kerr or Kerr-Newman is not integrable in Frobenius sense. So what does integrable mean? Well, it means that if you take your E3 and E4, your two null vectors, you take the orthogonal space in the tangent space. Then this orthogonal space now doesn't span. It's not anymore the tangent space of a surface. So it doesn't. If you think of it as being a tangent space, it doesn't close when you come back. Okay, so it's not a surface. It's actually, so the way you should think of this. So really there is no surface here in this picture. You should think of it as a horizontal distribution, or a two-plane field is also called. And as a consequence, for example, chi, which you may recall, it's normally interpreted as the second fundamental form, right, of the sphere into the four-dimensional space-time along the two null directions, is not symmetric anymore. So it is not, in fact, a second fundamental form anymore. And the way it can be decomposed, in addition to the traceless part and the trace part, there is also an antisymmetric part that is denoted in my work with Klein-Sheftelis. This is denoted with an A trace chi. So it's really antisymmetric part, and it has the volume form of this horizontal field, this epsilon, the volume form AP. And so because of this, because of the non-integrability of the null frame, we find convenient to complexify our curvature and Ricci coefficients. And so if you do that, so if you take your alpha and complexify it with its odd dual, so plus I odd dual alpha with respect to the horizontal frame, you get the complex tensor that also satisfies the Tokowski equation. So this is really just a tensorial version of the standard Tokowski equation obtained by the physics literature. And now this is also transformed, also has a Chandrasekhar transformation. So this was obtained by the famous Roniaski and Ma in for the linear case in Kerr. Now, for the nonlinear case, it's not that direct. I mean, the definition is not that direct. You actually have to define it in a. You have to expand this product, because otherwise the nonlinear terms are not acceptable. But morally speaking, I'm not really. Sergio mentioned that, but I'm not going to say much more than say again, it's a rescale two derivatives of your A, and you get this quantity Q that now satisfies a generalized Reggie-Wheeler. So it's not anymore that's as simple as the Schwarzschild case. So it's not simply D'Alembert minus a potential equal to 0. but you have some extra term, which is some nabla dt derivative. So you have some time derivative, but with some I a cosine theta rho square. So you can see it's I. It's really the imaginary I, and a real function, and then some lower order term on the right hand side that I'm not going to say lots of details about that, but those are terms which involve up to 2 derivatives of A, and which have some phi derivative and again 3 derivatives, and B is a positive real potential. So this kind of structure, so this is what I'm going to call generalized Reggie-Wheeler equation that was obtained by Lafermont-Soloniaski and Ma. And one may really be worried about this equation because you have, for example, this first order term, nabla t. So if you remember, the Tarkovsky equation had an issue exactly because I had those first order term, and we had to do the Chandrasekhar transformation to eliminate this first order term here, right? So why? So then we did all this work of Chandrasekhar transformation. We still have this dt derivative. Well, but this dt derivative is much more special than the one in the Tarkovsky equation. It comes with the I, so with an imaginary function in front of it. So why is this any good? Well, because if you try to very schematically derive energy estimates for this equation, so you see this is the first order term, and I'm going to just collect the right hand side as lower order terms. Then how do you obtain the energy estimates? In general, when you have a wave equation, what you do, you multiply by dt. Let's say you have box of psi equal to 0, you multiply by dt of psi and integrate by parts. Here, these are complex tensors. So what you want to do is you want to multiply by nabla t of q conjugate, and then take the real part. And if you do that, you'll see that the first term precisely gets canceled out in this process. I mean, it is basically what I'm saying is that this left-hand side, the box minus potential plus a term of this form, has still good divergence properties in applying the divergence theorem. In doing the vector field method. So it's not like a magical cancellation. It's just that the structure is good enough. Is almost, I mean, for the energy estimates, it's almost like you don't have this this term there. And the right hand side, of course, it is still still a complicated issue because this at the level of 2 derivatives of A is at the same level of differentiability as Q. So there are cancellations happening on this part too, but for small angular momentum, you can think of this as being lower order term. Okay, so this is the case of Kerr. Let me finally get to the case of Einstein-Maxwell equation. Okay, so let's say if we have the Einstein-Maxwell equation, we have this gravitation and electromagnetic radiations interacting, and from what we know, from the Tarkovsky equations, satisfied by this alpha that represents the gravitational radiation, and we also have the Tarkovsky equation satisfied by beta f that represents electromagnetic radiation. So what we know that they satisfy separately two Tarkovsky equation if we are looking at them independently, and these two gravitational and electromagnetic fields independently. But if we're looking at the coupled thing, what we should expect is to have some Tarkovsky equation for alpha sourced by this beta f, and some Tarkovsky equation for beta f sourced by alpha. Now, why didn't I just put, why didn't I just put the beta f and alpha on the right hand side? Well, because these are two different objects. One is a 2 tensor, so alpha is a 2 tensor, and this beta f is a 1 tensor. So let's say to have an equation for a 2 tensor, here on the right hand side we should have a 2 tensor, and the way of taking a 1 tensor and letting it become a 2 tensor in the spheres is done by taking this kind of operator, this symmetric angular derivatives, or there's also d2 star. And similarly, if you want to take an equation for a 1 tensor sourced by you have your alpha, you should be your source, but alpha is a 2 tensor, and to let it become a 1 tensor, you can take the divergence, for example. So this is the kind of system that you expect to have with a q in front of it, because you know that if q is equal to 0, if you're in Schwarzschild, this should be 0. The Tarkovsky equation should have on the right hand side 0. Okay, so this is what you should expect, what you would expect. But in fact, the things are not quite that simple. In particular, this beta f is really not a good quantity to look at, because when q is different from 0, so if you're in Einstein-Nordstrom or Kerr-Newman, this quantity is not gauge invariant. So what does it mean to be gauge invariant? Well, remember we have this null frame, but what we can do, we can also move the frame. We can consider a general linear frame transformation. And you can, this is a sort of linear algebra kind of exercise. You can write down the most general null frame transformation that brings your E3, your initial E3/4 into a new E3 prime E4 prime, which are O epsilon close to the original. So if you transform with these quantities lambda, mu, and mu bar being O epsilon, then this modification is actually still a null frame. So it still satisfies, that E3 and E4 are null, and their dot is still -2 up to epsilon square terms. So it's still a good frame. So if something is non-gauge invariant, it means that if you compute it in one frame, in E3 and E4, it gives you, let's say, 0, okay, something that looks like it decays. But if you change the frame, then it's not 0 anymore, or its decay is just completely different. So if you have a quantity like that, it simply has you have no use of a quantity like that for, in the first part of the proof, like the one when you want to start with something, you want to start with objects which are gauge invariant, and then use the gauge to control everything else. So beta f is not good. And I'm going to define instead the tensor that is gauge invariant, something that doesn't change with this null frame transformation. So what you have to do is to define new a new quantity that substitutes the beta f. But actually, what it turns out is that in the charge case, alpha is also not as good anymore. It's still a gauge invariant, but it's not as useful. So what I did is just to define two new quantities. So the 2 tensor and 1 tensor. So the 2 tensor, if you know the notations, you can look at it and try to see what is the definition. But it's not that important. What is really important is that they both contain. So you see, this F contains electromagnetic components and Ricci coefficients, and the B contains curvature and electromagnetic components. So they're a mix. And they are gauge invariant, and they're related to the alpha, of course, by a certain relation. This kind of relation here. So you have in fact 3, if you want, 3 gauge invariant quantities of alpha, F, and B, and you have a relation between them. So really, the whole thing will be governed by a system of 2 wave equations. And then there is this sort of elliptic relation between them. And you may ask, okay, which one is the gravitational, which one is electromagnetic radiation? Of course, this is like asking, yeah, I don't even know how to compare it, but it's really, if we write the Einstein-Maxwell equation with the left-hand side equal to the right-hand side, but there is really no difference between gravitational and electromagnetic radiation in the moment you're looking at the full picture, both radiations coupled together. So it's like, really, it's like asking, if going here in this picture, as if the radiation here is the one coming from this one or this one. It's just, both quantities are intercombined, and you can see it immediately from these definitions that they are defined using both curvature and electromagnetic tensor. So they're both a gravitational electromagnetic radiation in a certain sense. But if you want, you can consider the 2 tensor to be the gravitational, just because we know that the gravitational field is a spin 2 field, and then the 1 tensor to be the electromagnetic radiation. But the moment you're considering them together, they're just all coupled together all the time. And so really, this is really halfway, like having the right definitions. I mean, the definitions of quantities that are gauge invariant, because the moment you have that, you can see pretty easily from the Einstein, as a consequence of the Einstein-Maxwell equation, that they satisfy a Tukowski type equation, which are coupled between them. So exactly the structure I said I would expect, right? So the Tukowski equation for B sourced by F, and the Tukowski equation for F sourced by B. And even more surprisingly, or in a certain sense, these black holes know they have to be stable, so they know that there has to be some cancellations. There is still a Chandrasekhar transformation in this case, in the Kerr-Newman, in the Rising-Norton and Kerr-Newman case. So here I wrote down explicitly just because, just for fun. But so these are the exact definitions of the Chandrasekhar transformation. So from B you define this one form of P, and from F you define these two tensor Q, and they are defined using this. So these are the three-sky bar of the background, right? So you're in linear theory. So this is the three-sky bar and three-sky bar of Kerr-Newman, or Einstein-Maxwell of Kerr-Newman, and these are this gamma bar is the R plus IA cosine theta function, and these two quantities satisfy a symmetric system of Reggie-Wheeler equation, Einstein-Nordstrom, and generalized Reggie-Wheeler equation, Kerr-Newman. And I'm going to write down, so what is the system, the symmetric system in Einstein-Nordstrom is this one. So you see on the left-hand side, you have the Reggie-Wheeler equation, and on the right-hand side, you have precisely the source that I was talking about, the divergence and the symmetric and the angle and the symmetric angular term, and the potentials are some positive potentials. And why is this, why am I saying that this system is symmetric? Well, because the right-hand side are adjoint operators on the sphere. So you can integrate by parts using the divergence and the symmetric tensor. And why is this of any help? Well, because if you want to derive energy estimates for this system, you have these coupling terms which interact. So of course you will not be able to close an energy estimate for one of these equations. So let's say you want to multiply the first one by nabla t, and then integrate by parts, right? So the left hand side, okay, it's fine, it's like in Schwarzschild if you want. But then the right hand side, you're going to have a t derivative of p and an angular derivative of q. So those are both trapped in the black hole. So these are you have something that depends on q, and you have no information on q if you only use the first equation. So what you have to do, you have to use both equations. So if you do that, if you multiply by nabla t p the first equation and by nabla q the second equation and sum them, then you obtain the right hand side this kind of term, like a term given by the divergence of q dotted with nabla t of p, and then a term given by the angular derivative of p and nabla t of q. And what you can do, you can integrate by parts in t. Basically, you throw the this nabla t here on the q, and you can commute, and then what you arrive to is precisely, so these two terms precisely cancel out because of the fact that these operators are adjoint operators of the sphere. Okay, so what you're left with, so you're not left with nothing, you're not left with like just nothing, you're left with some boundary terms. So this is going to modify the definition of the energy. So the energy is given by two positive objects minus like this kind of dot product. So you have to still prove that the boundary terms is positive, but it's something that you can do in the full sub-extremal case. And another way of looking at this, if you don't want to think of multiplying by nabla t integrate by parts, is to define a combined energy momentum tensor. So you sum the two energy momentum tensor of the two equations, which are defined in the standard way, and then you subtract this dot product, this sort of symmetric dot product, and what really the system being symmetric means is that this energy momentum tensor has divergence equal to 0 when applied to a Killing vector field. And so what you can do is that you can then use this combined energy momentum tensor to apply the vector field method to the full current and obtain energy estimates, Moravitz estimates. There's lots of work I'm not really mentioning, but that's sort of what you would do from that. Now, what about the gauge dependent ones? I'm going to say really like sort of briefly the way I did it, but this is one could have done in many different ways. So we've heard a lot about the double null gauge used in the case of Schwarzschild in the linear proof and also in the nonlinear proof. The way I did it was using the outgoing null geodesic foliation or Bondi gauge. Again, you could have done it in the double null gauge as well. And this, which is this kind of gauge that we've also heard about in some previous talks. And what you want to do, then you want to use this special solution, the pure gauge and the linearized Kerr-Newman. And here, the way I did it was to do some initial data normalization to obtain boundedness and some far away normalization here. So you take some last sphere and normalizing on this null hypersurface here. And the way you obtain boundedness is through some integration forward from initial data. So let's say if you have your control of the gauge invariant quantity, so you have your control of alpha, and you get this kind of decay in Bondi gauge in Bondi coordinates, sorry, R and U. you have some r to the 1 minus 2 minus delta, then you can, for example, impose at initial data a condition chi hat equals 0. Then the equation for chi hat, so this is the nabla 4 equation of chi hat, is sourced by alpha, and you can, it's given by this sort of equation. So you can see that since alpha, the case is r to the minus 2 minus delta, this gives you some r to the minus delta. You can basically integrate from initial data forward. You get, you have this sort of integration. You pick up some, something that looks like a growth in R, but there is an R square in the equation. So you obtain precisely the boundless even decay for the chi hat in this way with integration forward. The problem with integration forward, though, is that some quantities, so most quantities get good decay in doing this way, but some quantities don't. For example, the omega, so I'm going to denote omega bar check, so this is really the omega bar of the linearized solution minus the background. This one verifies an equation that doesn't have an R inside the derivative. Okay, so it's only dr of omega bar check which decays. So if you integrate forward, then you just don't get, you cannot get any decay in R if you integrate forward. So that's the reason why you want to use some far away normalized gauge that is instead done by integration backward from far away. And but now the choices of gauge are much more trickier, because even if you start with if you use the same that I just showed, so let's say chi hat is equal to 0 far away, and you want to integrate backward, then if you're integrating backward, now you have to be careful that your right hand side is always integrable in R. So you see here, if you want to use the same equation, now you have this R minus delta, which is non-integrable if you integrate from far away. So you have to get now combinations with integrable right hand side. And something that you can impose is that the trace chi and trace chi bar is the same. So the mean curvature of these spheres is the same as the one in the background, so in Rice and Nordstrom. And this was the same choice as Kahneman-Stiftel. And then something in addition, in the electrovacuum case, you also have to select, and choose, find really some equivalent of charge aspect function and mass charge aspect function that decay, that have integrable decay. And there is one that transports optimally in L equal 1, and the other one that transports optimally with all L. And so in this way, and those are the ones that you want to impose to be 0 in the far away slice. And now you can see, so we can check now if you integrate from the far away null hypersurface backward. Now the omega bar, the same kind of integral, now will give you a decay in R, because you're integrating from a large R, and integrating from a last slice to a large R. Okay, and now I'm going to finish with just mention a little bit about what happens in Kerr-Newman, because as I mentioned at the beginning, there is no mode stability result for Kerr-Newman. If we go to this book of Chandrasekhar, and at the page 580, we see that he writes the methods that to be so successful in treating gravitational perturbation of Kerr do not seem to be applicable for treating coupled electromagnetic gravitational perturbations of Kerr-Newman spacetime. And what he does, you see here, he starts deriving the Tokowski equation. So the same thing he did for the Kerr, and then the last two lines, he says all efforts to decouple these equations were not successful. Numerous other alternative manipulations were equally unsuccessful. So what happens? What's the bad story in Kerr-Newman? Well, remember, in the mode stability, one studies solution to the Tokowski equation of the separated form, right? So you have some separation given by your T and phi symmetry, and then some function of R and function of theta. And the Tokowski, once you have this ansatz, you plug it in the Tokowski equation, you obtain radial ODE for R, but also an angular an angular ODE for S. And this is the definition of a spheroidal harmonics. So that's what is called a spheroidal harmonics, and there are eigenfunctions of this sort of funny Laplacian. And of course, if A is equal to 0, you can see that this reduces to the spherical harmonics. And now spin-weighted spherical harmonics are basically the eigenfunctions of Laplacian defined for different tensors on a sphere. And they are, and for those quantities this is basically it's called the Hodge theory on the sphere, they are related, they can be related, so different spherical harmonics of different spin, which means for the Laplacian refer to different tensors, are related to this kind of operator, the divergence and the angular symmetrization, which is the adjoint operator of the divergence. But the problem is that if you're in the axially symmetric case, so when A is different from 0, then you don't have this relation, this simple relation anymore. So you see, when they were doing this, the analysis, the mode stability analysis, Rice and Nordstrom, where it's spherically symmetric. So if you have your Tokowski equation sourced by a divergence here of a spherical harmonic of spin 2, this can be written is proportional to a spherical harmonic of spin 1, and similar for the spin 2. So you have the two equations decoupled. If you're in Kerr, well, you only use the spin 2 because you only have gravitational radiation. So the problem in Kerr-Newman is that now you have the interaction of these two things. You have a Tokowski equation source of a spheroidal harmonic of spin 1, which in principle is sourced by a spheroidal harmonic of spin 2, but now this you're not able to write it in terms of spheroidal harmonic of spin 1. So these two equations do not decouple. And so really the point here is that the mode decomposition is not your friend. You're actually, and in trying to decompose in modes, you're making these equations unsolvable. So what about instead the physical space analysis? Well, this is something that I've been doing in the past few years. And so what you obtain in this case is a generalization of the symmetric system in Rice and Nordstrom. Now this is a symmetric system of generalized Reggie-Wheeler equation. So remember in Kerr you had this kind of equations, actually the second one here, with the box, a potential and a nabla t derivative sourced by some lower order term. Now here we have a combination of what happens in Kerr and what happens in Rice and Nordstrom. So the left-hand side is this generalized Reggie-Wheeler left-hand side, which is just like the one in Kerr, so it has good property. But now on the right-hand side, you have this coupling that is now a little bit more complicated. So you see involves this gamma and involves this eta bar, which are non-zero anymore in Kerr-Newman or in Kerr. But nevertheless, this exact combination of this, you see, this is this function gamma bar, and this is the function gamma to the third, and this exact combination makes the whole system symmetric. Now, symmetric with respect to what? There is no integration on the sphere anymore, because remember, there's no sphere anymore. So we cannot say that those are joint operators on the sphere. But what this system is symmetric with respect to integration in space-time. So as a space-time integral. So this divergence and this angular derivative are now combined with this lower order term involving eta and eta bar. They are now a joint operator with respect to a space-time divergence. Okay, so you cannot integrate on the sphere anymore, but that's not a big deal because when you do space-time estimates, at the end of the day, you always integrate in the space-time. So what you have to do, you have to directly integrate the space-time. You cannot integrate first in the spheres. Okay, and so why? So just as a structure, see, this is a first order term, these are the coupling terms, and these are again the lower order terms, which I'm not going to mention. So why are these quantities, then why is this right-hand side then good? Well, because if we try to do the same thing, doing energy estimates, multiply by nabla t p bar the first, by nabla t q bar the second, and sum these two equations. Now, the first order terms, as I said, this part is fine. And what about the right-hand side? So I'm trying to show you what happens here. So if I take the right-hand side, I take the real part. Again, I'm going to integrate in t. I'm going to throw the nabla t derivative into the q. And now what happens is that this function, gamma to the third, rho to the 5, this function here that happens to be on the right-hand side of this equation, is precisely the one, so as a certain angular derivative that can be written in terms of omega, of eta and eta bar. And it precisely gives, when combined with the right-hand side of the equation, you see with -1/2, eta bar -5, and -3/2. When you combine them, you precisely end up having this combination of the angular derivative and eta plus eta bar, which is exactly the one that gets cancelled. So gets cancelled meaning give you a space-time derivative at the end of the day. So you can, at least for small angular momentum, you can still define a new energy obtained by these boundary terms, which is still positive definite. Okay, and really, I want to conclude the last 5 minutes mentioning how then one goes on to, these are the kind of the sketch how you do energy estimates, but then really, in Kerr-Newman, you cannot close the energy estimates by themselves. You really have to have the Moravec estimates as well. And here there is a problem, because most works in to obtain Moravec estimates, so integrated space-time estimates, are done using Fourier transform or some sort of pseudo-differential operators, and most notably work by the Fermat-Soniaski, Schlapentov-Rothman in the full sub-extremal range. And of course, just this is that's the only proof to obtain the full sub-extremal range. But because of this issue of separability in modes, interaction between spin 2 and spin 1 field, that's not what I want to avoid doing that, because then I don't know how to make this spherical harmonics interact. I'm not saying it's impossible, I'm just saying that I don't know how to do it. So if I don't want to do that, I would like to have a physical space analysis where I don't have to really mention spheroidal harmonics. And fortunately, there is a work that only works in for small for very small angular momentum by Anderson Blue, that obtains this physical space estimates in Kerr for the wave equation, and a very beautiful work. And this kind of method really makes use of the Carter tensor. Of course, also the Fourier transform uses the Carter tensor in the fact that the equation is separable, but the physical space analysis, it uses it in a different way. And try to describe very quickly how it is done. And just as a reminder, we have two killing vector field in Kerr or Kerr-Newman, the dt and the d phi, and there's also this killing tensor, right, the Carter tensor that satisfy the killing equation. And this is the fourth constant of motion, so like the mass, the energy, angular momentum, and then you have this fourth constant of motion, which allows the integrability of the geodesic flow. And you can write it explicitly, right? So you can write that this Carter tensor is given by minus a squared cosine squared theta, the metric, plus this combination of theta and phi, which are really the d theta and sort of d phi derivatives. And associated to the Carter tensor, one can define a second order differential operator given by two derivatives and a contraction. And this is given by D'Alembert. And then the following modified Laplacian operator. So you can see from here that if you're in a Schwarzschild, so you don't have this term, you only get the standard Laplacian. But in Kerr, you get this modified Laplacian. So this is the first two terms of the Laplacian, then you have this additional two terms. Okay, and what happens, what was observed by Carter back in I think it's 1968, was that in the vacuum space-time, the second order differential operator K associated to the scaling tensor field commutes with the D'Alembert. Okay, and so as a consequence, you actually deduce that this modified Laplacian commutes with, it's a conformal symmetry. So it commutes with rho square D'Alembert, where rho square is r squared plus a squared cosine squared theta. So O is a symmetry operator. And this was used crucially by Anderson Blue by writing the D'Alembert operator as some dr derivative, and then an additional second order operator in terms of dt squared, dt d phi squared, and O. So in particular, whatever is left in the D'Alembert can be written in terms of these four second order symmetry operators in Kerr. The dt squared, dt d phi squared. These are coming from simply twice taking a killing vector field, and then the fourth one is this O, this modified Laplacian. And so they use these differential operators to construct a multiplier in derivation of Moravec estimates that treats all frequency ranges. So there is no frequency. In fact, there's no use of frequency as opposed to the frequency analysis that let the dt transform into an omega, the d phi into an m, and the O will correspond to the capital lambda, to the separation constant. And now if I want to use this to apply to the case of Kerr-Newman, well, I may immediately have a first obstacle, is that in general, this Carter differential operator fails to commute with the D'Alembert operator if you're not in vacuum. In fact, you can do this computation, again, I don't recommend, but you can do it explicitly. It's not that hard to see that when you start commuting this operator, you get a bunch of Ricci curvature and even Ricci and Ricci scalar. So what about if you're a solution of Einstein-Maxwell equation? Maybe this is zero. Well, no, this is non-zero in general. You still have you have some simplification because this Ricci scalar is 0, the divergence of Ricci is 0, but you still have some commutator. But what you obtain is that in the case of Kerr-Newman, so in the specific case of Kerr-Newman that has the structure of the Ricci curvature of the Carter tensor, you have the cancellation of this commutator. So there is this K, and therefore this modified Laplacian commutes with the D'Alembert, so it can be used. So this method of Anderson-Bloom can be applied to this case, to the case of Kerr-Newman. And with this, I'm going to again I'll leave with the conclusion, and I'm going to end here. Thank you.
So, are there questions either in the Zoom or in person?
I saw something.
Oh yeah.
I saw. No. I thought I saw something.
Oh, there is a question in the chat.
If you read the slides correctly, the quantity frac F, frac B are quadratic in Maxwell center. Does this mean they managed to rapidly to consider perturbation Schwarzschild and Maxwell theory? They're not quadratic. Let me go back to the slide. They're not quadratic. They're linear terms. So let me. Oh yeah, sorry. Let me just 1 second. You can do two things at the same time. So the question is about F, the quantities which I passed clearly. The quantities F and B. So this Mach frac F and B here. Defined in perturbations of Schwarzschild, Nordstrom and Kerr-Newman. Peter's asking if they're quadratic in so let me if I can see if I now the question if they're so I say that's quadratic in the Maxwell-Einstein terms, but they're not quadratic, so they look quadratic, but they're not, because you see the beta F is 0 in the background, and you're taking angular derivative, so this is a linear term. Now this beta F is 0 in the background, but eta is not in. So this is the full definition in Kerr-Newman. Let's say in Rice and Nordstrom, yes, this term you wouldn't have this term. This term would be if you're doing linear theory. In Rice and Nordstrom, you don't have this term. But in Kerr-Newman, this term is linear because beta F is 0 in the background, but eta is not, right? So eta goes like A over R squared. And then this quantity here again looks quadratic, but it's not, because chi hat is 0 in the background, but rho F is not. Rho F is Q over R squared in Rice and Nordstrom. So this is still linear term. And the same thing happens here because rho and rho F are non-zero in the background. So they are given by some M over R to the third, and then some Q squared over R squared, and the beta and beta F are 0. So these are linear quantities. And the only thing is that the second term in the F will be quadratic in the case of Rice and Nordstrom, but I guess here I wrote it to the general expressions in Kerr-Newman.
Yeah, Lars.
Yeah, so very interesting talk. So I was wondering, so the system that you get is not separable, and I guess, but I mean, you eventually you use a symmetry operator. I mean, you use the Carter operator, but so that is a symmetry operator for the kind of wave operator that appears in the system and not for the whole system. Is that correct?
Exactly. Yes, that's correct. Yeah, yes, absolutely. In fact, yeah, that's something I didn't mention. Just
and I mean, so what I wanted to ask is that I mean, the fact that this works, that you can still do this. What's the reason for that? I mean, that you have, is there a reason that you have like some smallness in the part that's not symmetric under this operator, or what could you comment on that?
Yeah, so the first comment is precise. So maybe I'll repeat or rephrase the question so that maybe just for the sake of everybody. So you see here, what I've said at the very last part of the talk is that I can find this operator that commutes with the D'Alembert, but very rightly, Lars points out that this doesn't commute with all the other things that you have, right? And most notably, I mean, especially if you're looking at the small angular momentum case, which I am anyway, the most problematic is this right-hand side, of course, right? This is a divergence. So this doesn't commute. I mean, if you're trying to apply the Laplacian, this doesn't even commute in Schwarzschild, because you have, or in Reisz-Nordström in the spherical symmetric case, because this is, you have some Gauss curvature terms that pops out. So so basically, you can see that what I really have to do is I have to take this modified Laplacian and then correct it with lower terms depending on the Gauss curvature. But in a certain sense, again, because of this problem already appears in Reisz-Nordström, we can even ask ourselves the same question for this kind of the system in Reisz-Nordström, this one here. So you see that if you can, in a certain sense, in Reisz-Nordström, maybe you don't do it directly of applying the Laplacian, but it's really like applying the Laplacian to this equation. And then you have this divergence, Laplacian applied to a divergence. You pick up some Gauss curvature terms. And the reason why this works is, well, I guess it goes back to the fact that there is a physical space structure, again, that can be sort of expressed into this combined energy momentum tensor. That in the case of Reisz-Nordström, it's really pretty simple to write. It's really this one. And in the Kerr-Newman case, you have so basically, I don't know if that's clear, but you're modifying what you have to do. You have to modify by something that is non-small, even in Reisz-Nordström, for something that corrects this deficit of commutation because of your of the right hand side of this divergence and angular terms on the right hand side. So that's what you have to do in Kerr-Newman too. I mean, but to apply your method, like your Anderson-Blue method for Kerr-Newman.
So and this modification is done. Is it a modification of the operator, like the wave operator, or is it?
No, it's so basically you apply the O. So I guess the one in your notation would be like your Q, right? So
yeah, okay, the symmetry operator. Yeah.
Modified Laplacian, and then you have to add like plus or minus. I mean, you have some lower terms. So the modified Laplacian is two derivatives. It's at the level of two angular derivatives. You have to add some extra Gauss curvature and as a potential, basically. So with no derivatives. So it's a modified Laplacian with you modify the lower derivative. So no derivatives.
And this has better commutation properties, or
sorry, you say back.
I mean, so when you do this modification, what is it that you achieve, so to speak? Is it that you have better
what I achieve
commutator properties, or what?
So what I achieve is I take my system, what I call this system of generalized algebraic equation. I apply this operator, and now this new O, let's say this modified, this O hat, if you want, of P and O hat of Q, these two new quantities, they also satisfy a system of generalized algebraic equations. So they are a system. So now this modified operator is a symmetry operator for the system, not for the wave equation, but for the system.
Okay, very interesting.
So that's where you will have to apply like your method. Basically, you commute with dt, d phi, and then you have to commute with this modified operator. And in all this, you create lower term in A, which again, so that's why small angular momentum is of course crucial. But yeah.
Okay, thank you very much.
Yeah, thank you for your question.
There's a raised hand by Siama.
Oh, hi, Ella. Very nice talk. So, yeah, I want to ask, so can you briefly comment on the restriction of angular momentum A and the charge Q, if you have any restrictions on those two parameters or not?
Yeah, so as I mentioned, so maybe I was should have said it, yeah, more clearly, because it's crucial. Like the angular momentum has to be very small, so it's very small rotating, very slowly rotating. Because of, I mean, there are many reasons for that, and most not. I mean, of course, since I'm applying Anderson-Blue method, that's also for small angular momentum, and there is yeah, it's uncountable, like I don't know the number of places where this is used. Instead, for the charge, there is no restriction for the charge, because you see the charge, I mean, no restriction, meaning the sub-extrema range, because this really relies, I mean, the charge gives you the problem already in Rice-Nordstrom, and so the point of the Rice-Nordstrom is already has been solved by the fact that you can define this combined energy momentum tensor, and you can show that the modified energy is positive definite for the full sub-extrema range of Q. So that basically goes through in this case as well, but the angular momentum has to be very small. Yeah.
So somehow this symmetric hyperbolic property is preserved in the Kerr-Newman case, and so you can treat the large Q in the Kerr-Newman case as well.
Yes, exactly. So yeah,
but small a.
But not a, yeah, not a. I mean, it's just the problem with a is more fundamental in a certain sense, yeah.
Okay, I see. Thanks. Yeah.
Thank you.
All right, well, it seems there's no more questions, so let's thank Elena for a brilliant talk.
Thank you.